This video is on inverses of functions. An inverse function is a function that undoes the action of another function. In the original function, each operation that is done to x is undone in reverse order to x in the inverse function. So for example, y equals 3x plus 1 and y equals x minus 1 divided by 3 are inverses of each other. In the first equation, x is multiplied by 3 and then has 1 added to it. In the second equation, each operation is undone in reverse order. So instead of adding 1, we subtract 1, and then instead of multiplying by 3, we divide by 3. So x times 3 plus 1 is undone by x minus 1 divided by 3. Everything that was done to x is undone in reverse order. So here is a graph of these two functions. So the red graph, the red line, is y equals 3x plus 1, which should be familiar to you, and the blue line is y equals x minus 1 over 3, or 1/3 x minus 1/3. So notice at the table of values here, notice that the x and the y values are switched. So one ordered pair for the red function is 1, 4. Another corresponding ordered pair for the blue function is 4, 1. And in fact, that's true for all of the ordered pairs listed here. This means that the graphs of these two functions are going to be symmetric about the line y equals x, which you can see in this graph here. So each point on the red line, when it's reflected over the green line, lies on the blue line. So this is the line y equals x. And when you switch the x and y values in the red function, you get the blue function. So that's one way to find the inverse of a function graphically, is to actually graph those points. To do it algebraically, here's what you would do. We're going to start by replacing f of x with y. Switch the x and the y in the equations. In the equation, solve the equation for y, so isolate y, and then replace y with this notation right here. So it looks like it's f to the negative 1 power of x, but it isn't. This is actually inverse function notation. It's read f inverse of x or the inverse of f of x. Recall that sometimes a negative 1, what looks like a negative 1 power, can actually mean the inverse of something, and that's true for functions as well. You can determine if two functions are inverses of each other by showing that their compositions are both equal to x. So if two functions are inverses of each other, then f of g of x is equal to g of f of x, which is equal to x. And here's the same thing written in the other notation. So when I do one composition, it's equal to x. When I do the other composition, it is also equal to x. Let's see what that looks like with the two functions we've been working with. So let's let f of x equal 3x plus 1 and g of x equal x minus 1 over 3. Then f of g of x is equal to this. So I'm taking g of x and I'm putting it into f for x. So 3 times the quantity x minus 1 over 3 plus 1. And then when I simplify that, my 3's cancel. X minus 1 plus 1 is equal to just x. Same way, when I put f of x, that is 3x plus 1, into g of x for x, I have 3x plus 1 minus 1. My 1's give me 0. 3x over 3 is equal to x. So that's an algebraic way to determine that two functions are inverses of each other by showing that their compositions are both equal to x. Let's take a look at a couple examples here. We need to find the inverse of f of x equals x squared plus 4, determine whether the inverse is a function, and if so, we're going to write our answer in inverse function notation. So to start with, I'm going to do this algebraically. So I have f of x equals x squared plus 4. So my first step is to replace f of x with y. Second step is to switch x and y. So instead of y equals x squared plus 4, I'm going to write x equals y squared plus 4. So those are actually, as they are right now, those two would be inverses of each other. But let's go ahead and solve this second equation for y. So subtracting 4 on each side. and I'm going to kind of flip it over the equal sign so I get my y on the left. To undo this squaring of y, I'm going to do the square root of both sides, and when I do that I need to do the positive or negative square root of x minus 4. So let's go ahead and graph that and see what that looks like. So the positive is the square root function that has a vertex at the point 4, 0, and would continue something like this. So that's the positive square root of x minus 4. The negative square root of x minus 4 is going to look something like this. Okay, and as you can see from this is not the graph of a function. This actually fails the vertical line test. So this is not a function because it fails the vertical line test. Notice also, and I think as long as we're here, let's go ahead and take a look at what the original function, this function here, looks like. So if I were to graph that, and I'm doing this is actually not a part of the problem, I'm just kind of doing this for fun. So here is the function f of x equals x squared plus 4, and I actually like this because you can see that what we graphed, even though strictly speaking it's not a function, it is still a reflection over the line y equals x. It's almost as though I were taking this original parabola here, and if I flip it over the line y equals x, I get this sideways parabola here, which unfortunately is not a function. One thing I will say is we can make this a function if we restrict if we were to restrict the domain, if we were to say that this is only going to be equal to y equals the positive. Actually, if I restricted the, let me take that back. If I were to restrict the domain of my original function and say x can only be numbers that are greater than 0, that would be this piece of the graph right here, greater than or equal to 0, then when I do the inverse, it would only give me this, and that piece right there would indeed be a function. But as it's written, this is not a function. Take a look at our second example here. It says determine whether f of x equals the cube root of x plus 1 minus 2 and g of x, which is x plus 2 cubed minus 1, whether they are inverses of each other using composition of functions. So in other words, I need to find is f plus g of x equal to x, and is g of f of x equal to x. So let's go ahead and do that. So this is a little more complicated because we have some cube roots here. So I'm going to draw some circles. So I need to take g of x and put it into f for x. So that's going to be I have the cube root of, and instead of x, I'll write x plus 2 cubed minus 1, so that's x, and then here's the plus 1 that's also under the cube root sign, minus 2. So that's putting g into f. Let's go ahead and clean that up a little bit. So the cube root of, now underneath the radical sign, I do have a minus 1 and a plus 1, so that's x plus 2 cubed minus 2. And taking the cubed root of something cubed gives me just the radicand, so that would be x plus 2, and then I had this minus 2 out here, and that is indeed equal to x. So halfway there. So f of g of x does equal x. Now let's do it the other way, and let's take f of x, which is this function here, and let's put that into g for x. So instead of x plus 2, I'm going to take the cube root of x plus 1 minus 2, so that's x, and then plus 2, that thing cubed, minus 1. So inside the parentheses, I can get rid of the minus 2 plus 2, so that's the cube root of x plus 1 cubed minus 1. And then cubing a cubed root gives me just the radicand, x plus 1 minus 1, and that is indeed equal to x. So yes, these are inverses of each other because f of g of x is equal to g of f of x, which is equal to x. So in this video we took a look at inverses of functions, what inverses are, what that looks like graphically, what that looks like in terms of a table of x and y values, how to find inverses algebraically, and then how to use composition of functions to determine whether or not two functions are indeed inverses of each other.